Welcome. We are looking at phase field modeling. In the last lecture, we looked at two dimensional solution to the Cahn-Hilliard and Allen-Cahn equations. We started with a noisy profile and we allowed the system to evolve. In the process, we found that Cahn-Hilliard equation represents the microstructural evolution when there is phase separation, and the Allen-Cahn equation shows what happens in the case of order disorder transformation, how the domain structure evolves. So, in this lecture we are going to modify those scripts a little bit to study two problems that are of interest. The first one is the problem of Gibbs-Thompson effect, the second one is the problem of grain growth. So, before we go and modify the scripts for these two problems, let us discuss these problems a little bit and that will also help us formulate the equations. And the way I am going to formulate it is that they are the same as the Cahn-Hilliard and Allen-Cahn equations that we solved for last time, except for the initial profile. So, that is how we are going to formulate these problems. To do that, first let us start with what is known as the Gibbs-Thompson effect. Gibbs-Thompson effect is a curvature effect, or sometimes it is called the capillary effect. It is the effect on equilibrium in systems because of interfacial energy. So, what happens to the equilibrium in systems because of interfacial energy is what is given by the so called Gibbs-Thompson effect. For example, if you have a solid and liquid in contact with each other at their melting temperature, this temperature at which they will be at equilibrium. So, thermodynamically we define the melting temperature as that temperature in which the solid and liquid are in equilibrium. That is, at that temperature if you keep the solid and its melt in contact with each other, neither the solid will grow nor it will shrink. If it is above that temperature, then the solid will melt. If it is below that temperature, then the solid will grow. So, that is how we define the melting temperature. Now, this melting temperature is for a solid liquid interface that is separated by a planar boundary. So, it is something like this. So, if I have a boundary between solid and liquid, thermodynamically we say if you plot the free energies as a function of temperature. So, you have the, so this is the free energy. Suppose temperature is increasing this way, then this is the lower temperature. At lower temperature you want the solid to be preferred. So, this should be the solid free energy, this should be the liquid free energy. So, this temperature is the melting temperature. So, above melting temperature liquid has lower free energy, below melting temperature solid has lower free energy. So, these will be the states that would be preferred. So, this temperature is defined as the melting temperature, and that at that temperature if you keep the solid and liquid, suppose both of them are at Tm, then this interface will neither move to the right nor to the left. However, the temperature at which this happens is different if the interface is, for example, curved. Suppose this solid and this liquid now, the temperature at which they will be at equilibrium is not the same temperature as this. Let us call this as some Tm prime. If you do not want this interface to move, the temperature at which the solid and liquid will be equilibrium is basically determined by the curvature of this interface. Okay. Now, and this can be extended to other systems also. Suppose if you are looking at an alpha phase matrix in which you have a beta precipitate. If suppose you have an alpha phase in which you have another beta phase. Now, in these two cases the equilibrium composition of beta will be different. So, suppose if this is the case where the equilibrium composition of beta is Ce beta, in this case Ce beta will be different. So, it will be Ce prime beta. So, the Ce prime beta and Ce beta, how they are related can be obtained using thermodynamic arguments. We will do it as a tutorial. This C beta eta E prime is related to A the curvature of this and B the interfacial energy of the alpha beta interface. So, it depends both on gamma, alpha, beta and R, which is the radius of this precipitate. There is another way in which one can understand the Gibbs-Thompson effect, that is by looking at the phase equilibrium. Let us take the case when I have the equilibrium between the alpha phase. So, these are the free energy versus composition diagrams. Let us say that this is the free energy of the alpha phase, let us say that this is the free energy of the beta phase. Now, the composition at which they are in equilibrium is obtained by drawing the common tangent. So, this point will give C E alpha and this point will give me C E beta. This free energy is assuming that it is a flat alpha beta interface, or the radius of curvature is 0 or R is equal to infinity. Suppose there is a beta of given R, then this curve is shifted upwards, which means if you draw a common tangent between these two curves now, then that common tangent cuts both these curves to the left. So, this curve is now is C E prime alpha, now this is C E prime beta. So, any precipitate which has a radius R or a radius of curvature 1 by R will have a composition in both beta and alpha, which is higher than the equilibrium composition it would have if the interface is planar. Now, this is what also explains what is known as coarsening. Coarsening is when, for example, if you have an alpha matrix and in which you have lots of precipitates, lots of beta precipitates, right. So, the volume fraction of the beta precipitates, suppose the volume of beta is V beta, then as time proceeds the smaller precipitates disappear, the bigger ones grow at the cost of smaller precipitates and you get few big precipitates. So, V beta remains the same, here also the volume fraction is beta, the n beta in this case is higher than the n beta in this case. So, the number of precipitates decrease, hence the overall size increases, the overall volume fraction of the beta phase remains same. This is known as coarsening or Oswald ripening, and the way this happens can be explained using Gibbs-Thompson effect. So, how do we explain that? So, let us take a look at the case where I have say one big beta precipitate and one small beta precipitate. Okay. Now, I want to find out the composition of the alpha phase outside of this precipitate. So, we will go by the same common tangent construction. So, I have the G alpha. So, I have one beta which is for R equal to infinity, then I have, let us say this is R1, let us say this is R2 and R2 is less than R1. So, which means the curve corresponding to R2 will be higher than the curve corresponding to R1. So, if you now draw the common tangent between the two phases, okay. So, this is C alpha for R1 and this is C alpha R2. Similarly, so this is C beta R1 and this is C sorry, beta R2. So, if you look at the composition outside, so at these points you have C alpha R1 and here you have C alpha R2. C alpha R2 is higher value than R1. So, there is a concentration gradient, the concentration in alpha is like this, which means more atoms from here are going to move towards this, which means this then is going to shrink because it has to maintain this composition outside, and as it shrinks the equilibrium alpha is still going to be higher. So, as it shrinks this is going to be self reinforcing. So, this precipitate will become smaller and smaller and eventually disappear, and the diffusion will make this grow. So, this is the diffusion limited coarsening, and as you can see the driving force for coarsening comes from what is known as the Gibbs-Thomson effect. It can be shown that the change in composition, suppose for the alpha or beta phase I want to know the change in composition, then that change in composition, let us say is for the alpha phase, is given by an expression which is gamma, which is the interfacial energy. Okay. So, this is the alpha beta interfacial energy, and the curvature of the interface. Okay. In 2D it is nothing but 1 by r, and then C beta equilibrium minus C alpha equilibrium. So, that is the when the interface is planar between alpha and beta, what is the composition of alpha and what is the composition of beta. So, this is basically what the phase diagram gives, because phase diagram generally does not include the interfacial energy contribution. So, this times a quantity called chi, which is nothing but second derivative of free energy with respect to the composition at alpha in this case, and if you want for beta, then you have to calculate at beta. Okay. So, now let us consider a case. Let us go back to the problem that we were looking at. So, we were trying to solve the Cahn-Hilliard equation, and we took a profile in which we have put noise about 0.5. Instead, let us consider a system. Okay. Let us consider a composition. So, if you go across a line like this, you will see the composition. Let us say that the alpha composition is some 0.02 and the beta composition is 1. So, my initial profile is such that it is 0.02, and then at this point it is going to go to 1, it is going to remain as 1, and then it is going to come down. So, in such a case what happens, because this precipitate now has a curvature. So, as we did last time, we are going to describe a phase field model. So, composition is my order parameter. So, I have decided that I am going to describe my system using composition order parameter. It is a conserved order parameter. So, we are going to write Cahn-Hilliard equation later, and I am going to assume a free energy functional which is nothing but f0 of c, and f0 of c as usual I am going to assume that it is a c squared into 1 minus c whole squared plus kappa del c whole squared. Okay. So, integral f, so this is f by n v. So, this is per atom. So, f by n v dV is basically going to be the energy, free energy functional per atom. Okay. So, this is per atom. So, let me not put n v here. So, the by n v is basically given by this integral f dV, which means we are basically looking at the same free energy functional last time we used for getting this spinodal decomposition, except that I am going to choose the overall alloy composition in such a way that it is away from the spinodal line, but still it is within the two phase regime. In other words, if this is the miscibility gap and if this is the spinodal regime, previously I had started with a composition which was smack in the middle 0.5, about which I had some fluctuations, but now I am going to choose some composition which is on this side, okay, very low B. So, the composition is going to be very small. Now, if you consider such a scenario, then there is no spinodal decomposition, but because there is some excess saturation, super saturation in the matrix, matrix would like to be 0, but it is 0.02. So, this excess A atoms, the excess B atoms are going to come and grow this precipitate. So, after some time the precipitate is going to have a composition profile that looks like that. The reason this is going above 1 is that if you calculate, so del C beta if I calculate, then it will be gamma, gamma in this case we know is 0.33 divided by K is 1 by R. So, 1 by R, and in this case the equilibrium alpha and beta compositions are C E beta is 1 and C equilibrium alpha is 0. So, beta minus alpha is basically 1, and if you take the second derivative of this free energy with respect to composition, and if you put C is equal to 1 in this case. So, let us do that. So, 2 A C into 1 minus C into 1 minus 2 C is basically F prime. So, F double prime will be 2 A into 1 minus C into 1 minus 2 C minus 2 A, so C into 1 minus 2 C minus 2, so that is minus 4 A C C into 1 minus C. Now, if I put the composition to be C equal to 1, so this goes to 0, this goes to 0, this is the only case. So, I will get minus minus, so plus 2 A C which is 1. So, it is 2 A, and we have assumed A to be 1. So, it gives me a value of 2, and delta C alpha is also going to be the same because gamma and the same radius and the same and you can also see F double prime when C equal to 0, in these two are going to go to 0. So, when C equal to 0, again this is going to be 1, this is going to be 1. So, you get 2 A is equal to 1. So, you get the same thing. In other words, how much is this composition is increasing on the alpha side, the composition is going to dip by the same amount. So, that is the composition that will be in equilibrium for this given size. As the size becomes bigger, this comes towards 1 and this composition goes towards 0. So, that will be the equilibrium composition that you will achieve. Okay. So, this is what we want to see. So, as you can see, because I use the same order parameter, because I am using the same free energy functional in the implementation, if I just make the initial profile not a noisy one, but with a specific radius, then that problem will give me this solution. Okay. So, which is what we want to do now. So, let us go back to the code that I wrote last time. It was called 2D Cahn-Hilliard FFT, 2D CH-FFT. So, we will take the code. I have copied it into a script called Gibbs-Thompson.oct. So, we are going to modify the initial profile, and in this case we do not want to look at the microstructure because we want to see the compositional variation. So, I am going to plot the composition across this line. Okay. These are the only two differences. I am going to change the initial profile. Initial profile now is going to be a circular precipitate embedded in a matrix which has a small amount of supersaturation, and the plotting is going to be at the beginning of the simulation. I am going to plot it across the line. At the end of the simulation, again I am going to plot it at the central line, and we will look at the composition differences, and we will go look at how much is the composition change. In beta it should increase, in alpha also it should increase from 0. So, it should reach this value corresponding to the R value that we will use. So, that is the modification we will do and try to run the code. So, as usual, so I log into the machine, go to the relevant directory, and I have this code which is a copy of the code that we wrote last time for spinodal decomposition. So, I am going to change only the initial profile. Before doing that, let me take this half x, half n x, half n y and put them here, okay, because it is useful for me. So, I am going to define r, which is the radius of the precipitate that I am going to introduce. Let me say that that is 10. Now, we are going to define if less than r into r. So, what is less than r into r? So, I am going to put a precipitate with center at the middle, that is why I need half n x. So, how do I do that? I minus half n x, right, into I minus half n x. Okay. So, plus j minus half n y into j minus half n y. So, if that is less than r squared, okay, then I am going to make the C I j to be 1.0, else if C of I comma j is equal to 0.0, n for n for. Okay. So, this basically makes sure that the composition profile I have is circular, and now we want to only plot the profile. So, let me define a variable called C profile, that is half n x. Okay. So, and then I am going to plot C profile with a red line, and it will say initial profile. Okay. So, this is what I am going to do. There is no need for a pause, but instead I have to say hold on. I think there is a hold on somewhere up there. So, let me put the hold on here. And so, I am going to remove this. So, I am going to copy paste the plot here. Okay. So, the final line I want to plot with blue, and I want to call this as final profile. Okay. So, now the rest of the evolution is the same as earlier. So, let us look at the code once more. So, I clear the variables, I do not need more of, and I define a 64 by 64 system, and half n x is n x by 2, half n y is n y by 2. So, I define the radius of the precipitate, and I calculate from the center a distance which is of the radius r, and whatever points within that get a composition of 1, the rest of them get a composition of 0.02, right. So, we wanted to put a small far field composition. Okay. So, after that we plot the initial profile, we say hold on, and this is time increment, and these are the reciprocal space points a, m, kappa, they are all 1. So, and then we are going to run for some about 200 steps. I think I will make it 100 steps, okay. And we calculate G, we Fourier transform G and C, and then we evolve. This is periodic boundary condition implementation, and we evolve using the Korn-Hilliard equation, which is semi implicit Fourier spectral technique, and take the composition back to real space, and these two fars are basically the time loops, and at the end we come out and we plot the final profile. So, let us now run this code. Okay. So, there is a spelling mistake in else if, let me correct it. and if missing. Yeah. Okay. 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 So, we have to take the composition profile and we have to take along a line and call it as C profile. Okay. So, that is a mistake I made. So, let us now try to run it. Okay. So, now the code is evolving. The point behind this code is also to show that even though Cahn-Hilliard equation is meant for doing spinodal decomposition, if you are outside of the spinodal regime, which is like the growth regime, then the same equation should also describe growth, because we said that Cahn-Hilliard equation is just generalized diffusion equation. So, in the special case where there is no negative diffusivity, it should reduce to the usual diffusion equation. Okay. So, that is what we are seeing, and as you can see, the composition profile changes. So, if I go close to this and if I calculate, so I see that the composition has changed by, instead of 1, I get 1.016. So, we can calculate, we know in this case that 0.33 is the gamma, and the curvature is calculated by 1 by 10, and 2 is the second derivative of free energy into 10 into 1 minus 0. So, that is the, so if you calculate, it is about 0.016, and that is what this composition profile is showing, that the composition increases above 1 and it becomes 0.016 in the precipitate. So, this is purely curvature driven effect. For example, if you make the composition the radius of the precipitate to be say 20, then we should expect the increase in composition to fall by a factor of 2. So, let us see whether it does that, because now instead of 20 we should 10 we have 20. So, 0.008 is what it should be. So, if we run, we will see that, and in a similar fashion you can also change A and kappa. Using that you can change the interfacial energy, again you can do it as an exercise. If you change gamma correspondingly, the change in composition will also be there, it will also scale accordingly. So, as you can see here, so now I have precipitate composition. So, it comes to about 0.08 or something. Okay. So, and if you look at on the matrix side also, here the precipitate is too big as compared to my but here also you can see that it comes to about 0.009. So, if you equilibrate it, after a while it will come to 0.008, and the other profile will also go to 0.008. But 64 is a small system on which I have taken a very large precipitate, that is the reason why the diffusion fields are overlapping. So, it is not really equilibrating, but in the case of 10 on the other side also, you will see that on the matrix side also the composition shifts by the same amount. So, what is it that we are showing? We are showing that it is possible to use the same Cahn-Hilliard equation and also study systems where there is growth. It is very difficult to incorporate nucleation into phase field models, but in principle even that is possible. So, Cahn-Hilliard equation can study both nucleation and growth and spinodal decomposition. So, same equation can do both. But typically it is very difficult to get nucleation happen in the system. So, typically we throw in nuclei, like I have put a small precipitate, but the interfacial energy effect that is associated with the curvature of the precipitate, associated with the fact that the interface has an interfacial energy, there is a change in the equilibrium composition across this curved interface. The alpha and beta phases will have a composition which is different from when you have the planar interface, that is automatically captured. I do not have to do anything, the system automatically chooses the right composition. However, for the one dimensional problem that we have looked at, you can go back, you can take that problem, and there, irrespective of what the precipitate size you put, the composition of the precipitate will always remain at 1, the composition of the matrix will always remain at 0. That is because in that case there is no curvature. To define curvature you need 2D. So, in one dimension you do not see any curvature related effect. So, there you will see whatever is the phase diagram giving, that is equivalent to taking a planar interface and going across a line. So, 1D problem can be thought of as a special case of this planar equilibrium case. So, that is why you always get the compositions that you would get from the phase diagram construction. So, this is an important point to remember, and it is also very important if you are studying nanomaterials, for example. The melting temperature of nanoparticles is different from bulk materials. The composition across a nanoparticle matrix, the equilibrium composition of nanoparticle, and on the other side of the particle in the matrix, the equilibrium composition are different than if they are bulk systems. And you can prove as part of the tutorial to derive how much is the free energy shift. This is available in Porter and Easterling, and we will do it as a tutorial. You can calculate how much will be the shift, and you can show that it is related to directly proportional to gamma and inversely proportional to the radius of the precipitate, or directly proportional to the radius of curvature of the precipitate. And using typical values for interfacial energies for metallic systems, you can show that the relevant radius of the precipitate where Gibbs-Thomson becomes important is of the order of nanometers. So, that is why nanometer sized particles will have a strong effect. So, this is something that is known, you can look up online, for example. Gold nanoparticles, for example, melt at a temperature which is very different from where bulk gold will melt, for example. So, this excess energy associated with the interface shifts the equilibrium. That equilibrium could be in terms of the melting temperature, or it could be the equilibrium composition and so on. And so, that is obtained in a phase field model automatically. We do not have to do anything, the system will automatically choose the right composition for the particular size, an effect of which we saw last time. So, we saw initially there was a spinodal decomposition, and then there were different sized particles, and that microstructure started coarsening. That coarsening, like I explained, takes place through the change in composition on the matrix side, on the alpha side. So, the diffusion profiles that are set up because of the curvature related changes in composition in both the matrix phase and in the precipitate phase. So, which is what we saw last time, but it was a very complex microstructure where it was difficult to see what was happening. So, if we change the initial profile a little bit and show a circular precipitate in a supersaturated matrix, then we automatically obtain it. So, this is the part about Gibbs-Thomson. There is the other effect which is called grain growth. So, in the next part of this lecture, we will look at what grain growth is all about, and then modify our Kahn-Allen equation to look at grain growth. Thank you.